Now, today we're going to talk about buffers and how they relate to titrations. Before we do that, though, because this example is going to come up here when we talk about in this next section about buffers and titrations. Let's go ahead and do example 1 together. So it says a 0.1 molar solution of ethanoic acid, they give us the Ka, is mixed with a solution of 0.1 molar potassium ethanoate. Okay, and I have no idea what that is, what the formula is for that. I do, but I wouldn't expect you to know that. Okay, what's important here is know that it's with potassium. So whatever ethanoic acid is, I know it's not one of my 7 strong acids. So I know that equation is going to be Ha plus and then A minus. So this here represents the ethanoic acid, and then the potassium ethanoate, again, who cares what that formula is? It's going to be soluble, and ethanoate is going to be the A minus component. So when we're calculating in this case, they want to know the pH of the solution. We know that's based on the hydrogen ion concentration. So let's think about the Ka expression. The Ka expression is going to be H plus times the ethanoate ion over the concentration of Ha. Okay, and if you think about it, we know the concentration of the acid, and we know the concentration of the ethanoate. So we know this, the Ha, we know this, and they give us the Ka value. What's the only thing that's missing? Of course, is the hydrogen ion concentration. So this is just one of the problems where you literally just plug those numbers in. 1.8 times 10 to the minus 5th is equal to the hydrogen ion concentration. We'll just call that X. And the ethanoate is 0.1. The concentration of the acid is also 0.1. Obviously, the 0.1s cancel, which means that the hydrogen ion concentration, which again is equal to X, is going to equal 1.8 times 10 to the minus 5th. And then from there, we know we can get the pH of that. The pH equals the negative log of the hydrogen ion concentration. So negative log of 1.8 times 10 to the minus 5th is equal to 4.74. Now, when you're doing a titration, a very similar thing starts to happen. That at the beginning of the titration, let's say we're talking about a weak acid and you start to add a strong base to it. At the very beginning of the titration, again, think about that beaker that we drew. At the very beginning of the titration, the only thing you have are the acid particles. All you have is Ha. But as you start to add more and more base, you start to get more and more of this ethanoate or whatever this A minus happens to be. So no matter what point you're at during that titration process, if you know the concentration of the acid and you know the concentration of the conjugate base, you can find the pH. Okay, now remember, there's an easier way to do it than the way I just did it, and I did that on purpose, okay? Because remember that you can, when you have a buffer solution, remember that you have the Henderson-Hasselbalch equation, okay? So whatever the concentration of the conjugate base is, we could have used that in that previous problem. We could have said the pH of the equation is equal to the negative log of 1.8 times 10 to the minus 5th, which is how you would get the pKa, plus the log of 0.100 over 0.100. Okay, and notice that when you do that, what do you end up with? You end up with the exact same pH as what we got. Okay, so at any point during that titration, you can use the Henderson-Hasselbalch equation to find the pH of the solution. So if you've just added a little bit of base, let's say, and now you've got a little bit of A minus, well, of course, you're going to have a little bit of this, and you're still going to have mostly this, which means that, of course, the log of that number is going to be a negative number because your fraction is going to be less than 1, which means the pH is going to be less than the pKa. We've already talked about that. Okay, remember before the half equivalence point, the pH is less than the pKa. At the half equivalence point, we know the pH equals the pKa, and then past the half equivalence point, because now you have more of this than you do this, the pH is greater than the pKa. Okay, Now, same idea here. Whether you're starting with a weak acid and you add a strong base to it, or you start with a weak base and add a strong acid to it, again, the same concepts apply. Okay? That as you start to add the acid, again, a lot of times they use just NH3. So you've got NH3 particles. And then as you start to add the acid, here's our NH3s. As you start to add that acid, the NH3s are going to turn into NH4 pluses. And slowly over time, and again, you can use that Henderson-Hasselbalch equation as well to find the POH, just like we've done before. Okay, this paragraph here talks about the half equivalence point again. I think we've talked about that a lot already. Again, it's very useful on the AP exam to know that at the half equivalence point, the pH equals the pKa. And remember, it doesn't have to be just the half equivalence point. What if it's not a titration? If it's not a titration, there is no half equivalence point. Anytime that the concentration of the acid is equal to the concentration of the conjugate base, or anytime the base is equal to the concentration of the conjugate acid, the pH is going to equal the pKa. So whether it's a titration or not, again, many times it is, and as we saw in some of our previous problems from your homework, that a lot of times you're just looking at a pH curve. Okay? And then we've already seen this one as well, that sometimes you have like H3PO4. It can lose multiple hydrogens. Here's it's losing its first one, the second, and then the third as well. So you can have multiple equivalence points along the way. Okay, all right, let's do a couple of examples here talking about what I just said. So ethanoic acid has a pKa of 4.75. Find the pH of a solution that results from the addition of 40 milliliters of 0.4 molar NOH to 50 milliliters of 0.075 ethanoic acid. So here is where we really have to figure out how much acid do we have, and more importantly, how much conjugate base do we have. Because again, we're forming a buffer solution. So remember, you can use the regular Ka expression, or you can use pH equals pKa plus the log of the concentration of the conjugate base over the acid. Either one of those works. Okay, again, the more comfortable you become with this, the more you realize it's easier than using the regular Ka expression, but it doesn't really matter. So, let's think about this equation. Again, ethanoic acid, don't care what the formula is, and we're going to react it with NaOH. Again, notice on that last one, the first example that we did, we weren't reacting the acid with something else. We were just adding some of that soluble salt. Remember, that's two ways you can form a buffer solution. One of them is to react some of this with this, and then, again, some of this is going to go away, and you're going to create the A minus plus the H2O. Okay? And again, yes, I'm writing the net ionic equation. I'm taking that sodium out altogether. So, that's one way, and then remember the other way is to just add, like in the previous example, HA with H plus and A minus, and then you add some of this, and then you add like some Ka or NaA, something like that. Something that's a soluble salt that will add the conjugate base in there. So in example 1, we are reacting the acid with some strong base. The question is, how much of it is going to react? So let's take a look here. We've got 0.04 the molarity of the NaOH. So 0.04 times, and then the volume is also 0.04 in liters. So we have 0.0016 moles of OH minus, and then in terms of the acid, we have 0.075 times 0.050 equals 0.00375 moles. So now it's just a question of, okay, which one's going to run out first? What's our limiting reactant? Certainly it's 0.0016 of the NaOH. So this is going to go to 0. This is going to go down by 0.0016. So minus 0.0016 equals 0.00215. And then the A minus over here, which initially you have none of, is going to go up by 0.00215. So this is 0.00. Oh no, sorry, not 0.00215. Sorry, my mistake. Up by 0.0016, which means yes. So now we have the concentration of the acid. We have the concentration of the conjugate base. Okay, and excuse me, we shouldn't say concentration. Those are the moles. Those are the moles of each. Okay, and then concentration, we take those volumes and add them together. So that's over 0.090 liters over 0.090 liters. That's our new volume there. So 0.00215 divided by 0.09 equals, so this concentration, the concentration of the acid, so the pH is going to equal the pKa, 4.75, plus the log of, so the concentration of the acid is 0.0239 is what I get for the acid. And then for the concentration of the conjugate base, 0.0016 divided by 0.090 equals 0.018, let's say. Okay? Oh, let's use the same numbers here. Let's go 78. Okay, 0.0178. Okay, now, again, this isn't a titration, but if it were, we can see that the concentration of the acid is more than the concentration of the conjugate base. So at this point, you should be thinking, okay, we have not reached the half equivalence point yet, okay, because there's still more acid than there is conjugate base. Okay, and again, it's not a titration, but again, those are just some of the things that I think of. So I'm going to go 4.75 plus, and again, because that's less, my fraction is going to be less than 1, I should end up with a pH of less than 4.75. Okay, so plus the log, and now I'm going to go 0.0178 divided by 0.0239 in parentheses, and then I get a pH equal to 4.62. Okay, so I'm close to the pKa, which means I'm getting close to, if this were a titration, the half equivalence point, but I'm not there yet. All right, let's look at this one here. Very similar. Again, who cares what methanoic acid is? It's still a weak acid with H plus and A minus. Same idea as we just did before. So I'm going to do this one a little bit quicker. So 0.025 times 0.1. That means I have 0.0025 moles of this. And then 0.1 times 0.0239 equals 0.00239 moles of this. Okay, this is there's less of this one. So this one again is going to go to 0. This is going to go down by 0.00239. Okay, so 0.0025 minus 0.00239 equals a very, very small amount, 0.00011. Okay, and that also means the conjugate base is going to go up by 0.00239. So again, using the Henderson-Hasselbalch equation, pH is going to equal the pKa, so the negative log of 1.6 times 10 to the minus fourth, plus the log of the conjugate base on the top, which again, remember, went up by 0.00239. The acid, very, very small, 0.00011. And we're almost to the point here. Again, notice the moles here. The moles are pretty close, which means we're almost out of the acid. The acid's almost gone, which means in terms of a titration, where are we at here? We're right about here. We're getting real close to that big jump in our pH. We're well past the half equivalence point right here, which again, we're not doing a titration, but again, I always think of these questions in terms of titrations. So negative log of 1.6 times 10 to the minus fourth is 3.79, don't really care, plus the log of 0.00239 divided by 0.00011 equals, and again, I'm hoping that number is going to be higher than it was, and it is. It was 4.7, now it's 5.13. Okay, so at any point during that titration, or any time you combine an acid with a weak acid with a strong base, or a weak base with a strong acid. You just have to figure out how much of that original acid do I have left and how much of the conjugate base did it form. Okay, which remember, the first example that we did, where we didn't react to the ethanoic acid, we added a soluble salt that has that conjugate base already in it.